Okay, so now that you have it working, and now that you've seen the HTTP codes, if you still have your Python script running, hit Control-C. That's going to cancel it. All right? And now we're going to open up the code again. So the code that you have in your window should be the same here, right? Now let's take a look at this. We can only handle that index file. If we try to get anything else like the favicon that you saw, it's going to show error 404. Anyone have any ideas as to how to create another page with Python? Alex?
Make a new URL?
Yeah, make a new URL. So this URL's right here. If we add another, so say comma like slash text.html, and then you're going to have to add another comma and then just text as a string. So I'll stick it in here. It might be a bit difficult to see. So I'm sticking in first the URL that we want to match. So slash text, text.html. And then the next item in our list is going to just be text. So what this does is it says if the URL we want is our IP/text.html, we're going to use class text to generate that. We don't have a class text, so we're going to have to create it. To do that, we're just going to copy what index has. In Vim, an easier way to do that is hit escape. That enters command mode. Type Y, 2 down arrow. That's going to yank 3 lines. So 2 is 0, 1, 2, so 3 lines down of that top position where you were. Right? Then you can use the arrow keys to get to the bottom of it. Hit P, that's going to put it there. So that's how you copy lines in Vim. Or if it's easier, you can just type it out again. So for those of you who have successfully edited that script, you're now going to run Python on the script again. So Python, the name of the script, 80. It'll start running. And now you can still get to your original stuff that you had there. But what you can also do is you can also go IP/text.html, and that will give you the text generated by your second section. So put your hand up if your group has successfully gotten text.html. You guys do. The nerds I saw got it. For the camera, that's their team name. I'm not actually calling them that. Okay. So we are finally back on the same page. We're going to do the next section now, which is a little bit more advanced. What I'll ask you to do is please listen very carefully, watch very carefully. If at any point you think you're not getting it, put your hand up immediately so we can help you, okay? So what we're going to do now is let it handle not just text.html, but anything.html. So instead of what I have here is /print/anything. So we can add that. So you have your index, your /index, and then you also have the /text that we just added. So that's going to look like /text. This is what you've already added. You don't have to copy that. And then text, comma. The comma at the end is important. Right? And then you now can add this /print/, and what's this thing here? So these brackets tells it that this is a capturing group. So we're going to actually be able to get the text inside of this in a minute. This dot means match any character. So any character can go here, not just a specific one. And this star means any number of characters. So we can access basically /print/anything. And then right now I have print_text. This print_text class is going to access /print/anything. So add this to the end of your URLs. It's 2 things. It's the print/ and then this bracket dot star. It's also print_text. And also add this class, right? So below your text class, print text. And for now, you can copy the text. We'll talk about these differences in a second. Counselors, maybe go around to all the groups, make sure everyone's entering that okay? So guys, make sure you have this comma here, because even though it's split across multiple lines, it is just a list. So without this comma, it's not going to work. right? So you need a comma here. You don't put one at the end because it's the end of the list. Okay, it looks like you guys have just got it. Yes, you guys have just got it. Okay, so you guys are way ahead. So you can play with that. Try making a different URL. And what that is a regular expression. So if you look up regular expressions, for instance, in square brackets, ABC will just match the characters A, B, and C. So you can try doing something with that. So a lot of you are already starting to do this second part. A lot of you have done it. A couple important points to note. You have to add comma txt here. This is squiggly brackets, not round brackets. So what this does, when you get to it, is since this matches print/anything, that anything in this round bracket here is being sent to this text variable. Now when we call .format text, it replaces bracket 0 with the text that came from here, that came from here. So it's actually going to print out the URL that we just went to. And we can use that text variable in whatever other way we want within our Python file. So everyone has it. What did we notice? When we entered something in there, we were printing it out in the main web page, right? So we can use that as one way of getting input from the user, is just changing the URL itself. But that's not what we commonly do. What we commonly do is something like this. So right now it's not running, but in Google, if I go ahead and search Google for, say, deep. So you go to Google/search $Q equals deep. So that's how we pass arguments to web pages normally. And that Q is the argument, deep is the value. So now we're going to write Python code to handle that. So what you'll notice is, when you go back to your page, I don't have it running so I can't show you, but so your print/something, add $Q equals something. You'll notice that that's not on there. That's not printed, right? You see that? So that's because that is being handled separately by Python. Now we're going to find out how to handle that. So that, with the adding Q equals something, that was just to see that it's filtered out, right? So how we handle that is with this code. Can you guys see that okay at the back? So the important changes to note, we don't actually need to change this at all, right? So we can use any of these existing classes we've already made. In this case, I'm using the print text. The other thing that we're doing is we're using web.input. So web.input is what we use to get that argument, and it's web.input, note the brackets, .q, and that's for Q. So web.input.q, and that will give us whatever was put in for Q. So who has that working? We have two groups have it working for Q. You guys have it working. How is Otter doing? There's still 2 minutes. Do you guys have it working? Okay. So for those of you who do have it working, what you'll do is in here we have return hello world. That's for our index class. We're going to make a simple form. So change this to triple quotes so that we can actually go ahead and do multiple lines in it. And we're going to replace this hello world with a little HTML form. And that form looks like this. So inside our triple quotes, form action equals, and for the action, put the URL of whatever Q page you just made. Yeah, so like, for instance, with me, I did slash, I guess we could call it like print. Yeah, so like if I'd done print.html to handle my queues, then that's what I'd put. I'd put slash print.html. Yeah, so a lot of the groups are having some trouble with just seeing the raw code. what you can do to fix that is make it an HTML file by encapsulating it in HTML. So HTML and body, oh, not Brody, body. And then we're going to end those at the end as well. So slash body and slash HTML. There you go. So once you've done that, what happens when you go ahead and load your main site, so just the IP? You should see a form. Okay, so we've all got that working. So what did you observe when you went to your main page? You saw the form, right? And you entered text, hit submit, and that text was then handled by the Python in the page that's submitted to. So that's the basics of how forms are handled on the web and with HTML. And form elements are what runs most of the web-based software as a service cloud applications that we saw. Right? So for instance, you can even think of Google as something of a software as a service. And when we go into the Google main page and type something in, so let's look up like random text here. So in Google, if we look up some random text, then we see that as Q equals that random text. So we've just created what could be the backbone for Google, if only you were 20 years older. Any questions on that? So now we have to look into a slightly different element of programming, not just for the web and cloud computing, but also for high performance computing, and that is how to handle high demand. Right now we're just testing it with one user. We could have potentially thousands. So to handle high demand, we are going to start looking at parallel programming and efficient programming, and as well programming on high performance clusters. So that will be our next section. Okay, so we will start by talking about high performance computing in general, and we'll be using our SCINET supercomputer for that. So, anyone have any idea what a supercomputer is? Okay, I heard it's huge. It's not that. Any other ideas? Yes, Grant? High streams, so like a lot of data kind of a thing? Okay. Nicholas? Okay, so it runs complex programs really efficiently. Velo?
Yeah, it's the collection of multiple subcomputers or processors which act as one single computer.
Okay. Have you taken this course already? No? Yeah, so what Velo said, it's a collection of multiple computers or processors that act as a single processor. They're a single computer. That's very, very close to it. Yeah, so unfortunately, as of a couple years ago, computers really aren't getting any faster. If we try to clock them faster, they will heat up. In fact, there's an exponential relationship between clock speed and power dissipated. So if we tried to get double of what we're getting now, we'd end up with like 10 times the amount of energy, which means your fans would have to be running 10 times as much. If we tried to get, I forget the exact number, it's on the order of 10 times as much, our computer would get as hot as the inside of the sun. So we cannot speed up computers anymore. So unfortunately, a supercomputer like this would not happen. What we do get is supercomputers like this. We can't make one faster, so we can make many collectively faster. An example of that is SCINET. So SCINET is what we'll be using. SCINET is what we'll be seeing on Thursday. It's got a lot of RAM per node, a bunch of different nodes, a couple thousand of them, and even more processors within each node, a lot of storage. So it's got a bunch of different nodes, and they're all connected together using Ethernet like we learned about, and a bunch of more fast technologies. And each node is like a very powerful desktop. Yes? What's, P, where are you seeing that? Petabytes, yeah. So PB is petabytes, so like we have kilobytes, megabytes, gigabytes. The next one is terabytes, so that's 1,000 gigabytes, and then a petabyte is 1,000 terabytes. So it's 1,000,000 gigabytes.
That's a lot of gigabytes.
That's a lot of gigabytes, yeah. Yeah, we will be seeing all of those gigabytes on Thursday, right? So SciNet is a huge facility, lots of these, allotted storage, and it allows us to run very large programs using all of this, right? But it's not without its challenges. It is not this. So we can't just give it our lovely Python program and have what would normally take a couple days run in a couple milliseconds. The first thing that we have to think about is it is 3,000 nodes, almost 4,000 nodes. The reality of that is no one program can run on that many. We'll get to why in a bit. So what we do is, it's a cloud computing service. We share its computational resources. And the way we do that is with a queuing system. So let's look at it right now. So this would have been as of a couple hours ago. An example. Let's say someone says, I have this program to calculate something I need to. It's going to take 4 different nodes, and it's going to take 3 hours. And someone else says, I only need 1 node, but I need it for 7 hours, right? And they submit a bunch of other different jobs. And it's now up to this queuing system to try to figure out how can we schedule them all, given this is only 8 nodes, so a much more simplified version. And it would normally schedule them a couple days in advance, not just hours, right? So it schedules all these different jobs different users need to do to run on the various nodes that are available and try to minimize space that one isn't being used, right? So if we submit a 1 hour long 1 node job, it could go here. But as soon as we want it to be 2 nodes, it's going to have to wait till all the way back here before it can run, right? So that's the queuing system on a high performance cluster such as SciNet. Once the job is running, now we have to think about how do we use multiple nodes, right? Python is is a traditional programming language. So remember back in day 1 when we looked at assembly language and machine code and the CPUs that it ran on, right? Yes? Okay, so a node is one of these, right? So it's a bunch of different nodes. And these nodes are like little desktops, and they all are connected together, they run together, but they are separate machines, right? And each node has a bunch of different cores. So for instance, like you have dual core and quad core. SciNets have 16 cores, most of them. Yeah, so a node is like a separate machine. So when we're running Python, right, we have, say, our Python loop. And that's like that loop we looked at yesterday morning where we were summing up 1 to 100, right? It's looping back to that label. It's all in machine code. The machine code runs on 1 piece of RAM, and it's run by 1 processor. How do we write Python that's going to actually run on a bunch of different nodes and take advantage of this supercomputer capabilities? Any ideas? Okay, yeah, so Judith is reading it. Kelvin, do you have anything? You're kind of, sorry? Threading. Threading? Okay, threading. Have you taken this course too before? Yeah, so threading is one example. So you're both touching on it. Threading and in general parallel programming. So what parallel programming says is we can't write a program that runs on 2 CPUs. It doesn't work. CPUs are very intimately connected with themselves. What we can do is write 2 programs to run on 2 CPUs. So what we can do is write these 2, they run on them, and then we can somehow mix the data together at the end so that the 2 did the work of 1 in half the time. So that's where parallel code comes in. We run 2 pieces of code in parallel. So a very simple sort of pseudocode example is we're going to read some data, and then we're going to compute the data, and then stick that to a list, right? So it's going to create a list of 2. And then we do the same. We could do this in 1 program. We could read, compute, list, or we can do it at the same time on 2 different threads, as you were saying. It could also be on 2 different nodes entirely. So a thread is like running 2 programs on the same processor, which doesn't really help us because what a thread does is it alternates anyway. Since it's the same processor can't do two things at once. So a thread says, do this, now do this, then this, then this. So it runs them both just more slowly. With two different nodes, it runs them both at the same speed. Which one, however, is going to append to this list first? We don't know. We can't know. Processors run on their own. We don't have any way of synchronizing them unless we do that ourselves. So it might be this, and the worst part is it changes from run to run. So if it's this one first this time, it might be this one first the next time. That's what's called a race condition. So that's where we have parallel code. It's running at the same time, but we don't know which one's going to finish first. So we could have all kinds of different orders, and we'll see that for ourselves in just a minute. So parallel code is very counterintuitive, right? You think about programming, you think about running one command then the next. In parallel, it's all going at once. And there are a lot of subtle things that could go wrong. So we'll have to keep an eye out for that throughout the rest of this module. So let's start looking at what types of algorithms exist and what happens to them as we try to scale them up. So what's called embarrassingly parallel is where it's like two copies of the same thing, but they don't need to talk to each other. We can just do it at the same time. It does not matter. So an example I have is two people making two sandwiches, right? You don't need to talk about the sandwich. You don't need to use anything from the first to make the second. So two people making two sandwiches is just as good as one person making two, one after the other, right? So making sandwiches is an embarrassingly parallel algorithm. So you can use that next time, like, you're at home and it's taking one person forever to make the family sandwiches. You can say that's embarrassingly parallel. So we should make it more efficient. Most algorithms are not embarrassingly parallel. Most algorithms have a part that could be made parallel, but a part that cannot be. And so that part might be, and usually is, collecting data, right? So if, say, we use some algorithm to calculate different digits of pi, and it's a magic algorithm that will get each digit on its own, but it takes a long time to run. So we can get each digit separately, but we have to stick them together, and that part can't be done in parallel because of the nature of the fact that it requires all the digits that were calculated by the other processors, right? So that is what's called the sequential part. Sequential because it has to run sequentially on the same processor, one after the other. So this is the Greek letter alpha, and it represents a proportion. You guys familiar with proportions? No? So a proportion of 0 means that if alpha equals 0 and alpha is the sequential section, this should be sequential, no S, it means that the entire thing is parallel. If alpha is 1, it means the entire thing is sequential, so we can't parallelize any of it. If alpha is a half, it means that half the code is going to be sequential and the other half will be parallel. Right? So alpha, usually a decent alpha value is like 0.1 or less. So if 0.1 or less, that means that a tenth of the code or less has to be run in sequence. The rest can be parallelized. Make sense? So say if you want to make sandwiches and then put them in a picnic basket, which part is parallel? Yeah, making sandwiches. Which part is sequential? The picnic basket, right? Because it's the same picnic basket. We can't jam the two into it at the same time, otherwise it won't end well. If we do try to jam the two into the same time, we end up with a race condition because the sandwiches, neither of them can go first, so they'll just squish each other. Yeah, so if, say, it takes 5 minutes to make one sandwich and 30 seconds to put it in the bin, that means that we have, it's a factor of 11, which I don't want to calculate, 0.0909 repeating is our alpha, right? So given that time, actually that's not a factor of 11, that's 7. So that's even worse. But yeah, so our alpha is the proportion of time that is sequential. Make sense? The speedup is the serial time over the parallel time. What's that mean? The serial time is where we have just one processor, we have to do it all sequentially, even the parts that can be run in parallel. And then the parallel time is, given a certain number of processors, how long does it take? So if we have one person making two sandwiches, You make one, 5 minutes. You make two, 10 minutes. You put it in the thing, 10 minutes, 30 seconds. If you have two people, each one makes one, and they both take 5 minutes, then they put it in the thing, 30 seconds, right? The speed up is almost 2. It's not quite 2 because the 30 seconds stays the same. So it is 1030 over 530, right? And that would be our speed up. So say like an 8 times speed up means that your program runs 8 times as quickly. We actually have a limit. If our program has a certain part that is just sequential, we have a limit as to how much speed up we can get. And we get that limit by looking at it mathematically. So say TS is our serial time, right? So TS for the 2 sandwiches is 10 minutes, 30 seconds. If we want to get our sequential time, or our parallel time, what we have to do is take TS and multiply it by alpha. So alpha is the proportion that runs in serial, and that has to be the same amount of time. And we'll also have our 1 over alpha. This should be over p, not p times. Or sorry, 1 minus alpha, and that's the parallel part divided by p, and it takes that much less time because we have that many processors. So p is the number of processors. So for a sandwich, it takes 10 minutes is our serial time to make sandwiches. Then we divide it by 2. It takes 5 minutes to make to make both with 2 people. Everyone following so far? Any questions? So we have our sequential and our parallel time, and we can mathematically express them like this. Our speedup then is our serial time over our parallel time. Now this should also be over p. I made a mistake there. But as p approaches infinity, right, we're dividing this value, 1 minus alpha, by a bigger and bigger value. This is going to go to 0, right? And this goes to 0, so we just get over alpha plus 0, so that's just alpha. But TS over alpha plus 0 times TS, the TS's cancel out. So we get 1 over alpha. What does that mean? That means that the fastest speed up we can get is 1 over the proportion of sequential time. And that makes sense. If 10%, so if we have a alpha of 0.1 is serial, we can never get more than 10 times speed up, because more than 10 times speed up means that our serial section runs more quickly, right? That can't happen because that can't be parallelized. Making sense so far? Yeah. So this is what's called Amdahl's law. Oops. So Amdahl's law says that we have this limit on the amount of speed up we can get. That's the main reason that we can't use all 3,700 nodes on SciNet at once, right? And that's the reason that we do have that queuing system, and we don't just run it all 3,700 nodes at once. All right? There are a couple problems with parallel algorithms. So let's say we want to do an algorithm. We have a parallel section, a sequential section, another parallel section, another sequential section, right? This sequential section uses all the data generated by the parallel sections. But we have to wait until they're all finished before we can run this. And that means that we have a lot of wasted space. These 3 processors are doing nothing in this wait time. And likewise, when we repeat it again, there's an even more amount of space in which they're doing nothing. So data balancing is a very important thing in parallel programming. We want to make sure that these have the same amount of work, or as close as possible to it, so that we're not wasting all this time. Any questions on that? Yeah. Oops. Wrong mouse button. So, we're going to be trying out some of these computations, and we'll be using SciNet for that. So we're going to start with an SSH client again, so like PuTTY, and we're going to log into SciNet. Yeah, so this one we're going to do on our own. So head back to your own computer. So this is your host name. Leave the port as default, and you don't have to put in any SSH key. So just log into that host name. So log in as that up there, login.scinet.utoronto.ca. Okay, so what you're going to log in as, we have to distribute the different accounts that are available for SINAP. So what I can do is put that into the shared folder. I'm going to give you guys a number, okay? So I'll go down, use your number, log in with that account, not someone else's.